Hey everyone, welcome to homework two of my computational methods course. Here in part one, we're going to do part 1A, which is numerically demonstrate the central limit theorem, right? So we'll get into a lot of difficult things during this homework, but this one, fortunately enough, is pretty self-explanatory, right? So central limit theorem, what is it? Basically, if you have a sample, right, with a certain mean and a standard deviation, and you take a sufficiently large sample from the population, um, um, large random samples from the population with a replacement, the distribution of the sample means will approximately be normal distributed, right? So basically, if you take a ton of sets of data and those samples are sufficiently large, you will get normally distributed data. And normally distributed data looks like this. It's like a bell curve, right? And it's super useful for us. Because you can do a lot of statistical tests that assume normality. So if you have a normal distribution, um, it'll work. So to numerically do this, right, we're going to basically take a bunch of data sets, right? And if we increase the population, we're going to see that our histogram or a bar graph goes to a normal distribution. So let's get into it, right? So we're going to import our libraries. Right? It should be not sublets like this. Um, and then what we want to do is make a random, like make a variable for a random state. So it's going to be np.random state 123, and we're just basically going to use this RNG to make our random variables, right? So if you think about it, we're taking sets of data with populations, right? So we need to know the number of sets we're taking and then the number of samples in each of those sets. So let's just say for now that they're 10, we'll change them, right? But we have the number of sets, we have the number of samples, right? And to create our random data set, we're going to take the sets, we're going to make an array of size sets and samples, so 10 by 10, okay? Because they'll get 100 data points, and we're going to randomize that, right? So our data is going to equal rng.random, and then it's going to be of size n sets and n samples, right? And if I just wanted to make this more random, I could sum, I could just add this together, right? Because if you add two random data sets, the resulting data set is going to be inherently more random, right? And then if we go back to our CLT definition, right, it says the distribution of the sample means will be normally distributed. So for us, we want to find the average of our sets, right? Each set, we want to take the average of that, and that will be what's called one sample mean. Um, so the way we're going to do that is we're going to say our set average equals np.mean. So it's the mean of our data. Um, and um, it's just going to be the mean of our data, right? And then axis equals 1 because we want to do it for the number of sets. And so this is just going to be a list, right? And it's going to have the set average, right? And then, so to make our actual histogram, right, we need to know the number of bins, which is how you divide the ranges on the x-axis of our histogram. And then we need to know the counts in each of those bins, right? So we're going to say counts in bins equals np.histogram, right? And then we're going to use set average, and then we're going to use the number of bins that we want. So let's just say n bins equals 50, and there you go. And now we're ready to graph this. So we're gonna do our normal method. It's a figure equals make subplots, figure dot add, and then we're gonna add a bar graph where x equals the bins, y equals the counts. And then so let's go ahead and graph this, see what it looks like. So it looks kind of weird, right? But that's because we only have 10 we only have 10 sets of data, right? So let's increase the number of sets of data to 100. We're starting to get somewhere, right? Um, but not quite as normal as we'd like. And just to see, let's see what changing the number of samples in each set does to the data, right? It gets a little bit more normally distributed. I wonder if I make the number of samples really, really high. It's doing a bit better, but clearly the number of sets is what has an effect on it. So let's increase the number of sets by a lot. Okay, maybe I did too much. Um, Let me refresh this. Just reload. Give it a second. Okay, right. Let me decrease this, increase this. And there we go. Now we have a normal distribution, right? So we showed as we increase our population, our number of samples, we approach a normal distribution. Thank you guys for watching, and I'll see you guys in the next part. Thanks.